In this video, we're going to consider a few of the significant advancements in the history of decision-making. The fundamental problem with decision-making is it's not possible to know the exact consequences of the decision in advance. That makes it difficult to judge the best course of action. Blaise Pascal was a decision theory pioneer when he proposed his famous theological wager. It contrasted two possible courses of action. Either live as if God exists or live as if God does not exist. In Pascal's analysis, acting as though God exists produces an infinitely high payoff if you're correct, but a small cost if incorrect. In contrast, acting as though God does not exist produces a small benefit if correct, but an infinitely high cost if incorrect. Pascal's treatment suggested that decisions involving uncertain outcomes should be based on the value of each outcome weighted by its likelihood. Whichever action results in the greatest expected value is thus the best course of action. In the case of this wager, behaving as though God exists is the course of action with the highest expected value. Here's what this expected value theory looks like in monetary terms. Suppose course of action A has two payoffs. You gain $30,000 or you gain $40,000. Each outcome is equally likely with a 50% chance of occurring. The expected value of this action is $35,000, calculated as shown here. Compare that to action B, which has you with a 70% chance of gaining $20,000 or a 30% chance of gaining $50,000. Which action should you take if you can take only one? The expected value of action B is $29,000. So a rational man was expected to maximize his expected monetary value, and in this case, choose action A. Is that what always happens? Pascal's wager suggests people should be willing to gamble on an infinitesimally small chance of winning an infinitely large amount of reward. However, most people actually will not take this kind of extreme risk, suggesting that expected value approaches don't fully capture how people make decisions. Consider this situation, where instead of a choice between actions A and B, the choice is between A and C. Even though C has the higher expected value, many people would be expected to choose action A. Daniel Bernoulli helped illustrate the shortcomings of the expected value approach with his St. Petersburg paradox. Imagine a game of chance in which a fair coin is tossed repeatedly. You win $2 if a head appears on the first toss, $4 more if a head appears on the second toss, $8 more for a head on the third toss, and so on. The game ends the first time a tail appears. You keep your winnings to that point. What would you pay to play this game? This game has an expected value of infinity. Clearly, no one will pay an infinite sum to play this game. The key is people do not decide only on the basis of the probability of different outcomes alone. Instead, they weight the utility or goodness of those outcomes. Thus, expected utility theory was born. In the 20th century, von Neumann and Morgenstern formalized this general approach with a set of 4 axioms describing the behavior of a rational decision maker. First, the decision maker should have well-defined preferences. This is the completeness axiom. For any two options like apples and oranges, either one is preferred to the other or they're equivalent. Second, these preferences should exhibit a consistent rank, the transitivity axiom. If apples are preferred to oranges and oranges are preferred to bananas, then apples should be preferred to bananas. Third, these preferences exist on a common comparative scale. That's the continuity axiom. If apples are better than oranges, but oranges are better than bananas, then there should be a probability where receiving an orange is thought to be equivalent to a gamble on the likelihood of either winning the desired apple or losing and receiving only a banana. Finally, these preferences should not be impacted by irrelevant alternatives. That's the independence axiom. If someone prefers apples to oranges, apples should still outrank oranges, even if there's some broccoli lying around too. Von Neumann and Morgenstern showed that by following these principles, a decision maker would act to maximize his or her own personal utility function. You can think of the difference between expected value and expected utility as reflecting the value of non-monetary things. Consider home insurance as an example. Suppose the annual chance of your house being destroyed by fire is 1 in 10,000. But if it is destroyed, you lose $300,000. The expected value of the insurance policy is 1 in 10,000 times 300,000 plus 0.9999 times 0, which is equal to $30. So if you can get fire insurance for $30 or less, it's a good deal. Now, an insurance company may be willing to insure against the loss of your $300,000 house for $100 a year. According to expected value, you shouldn't insure your house. The cost of insurance, $100, is far greater than the expected loss of your house being destroyed by fire, which is only $30. The expected utility is different, however. Utility is the square root of income in this example. If you're wealthy, paying $100 only has a small marginal decline in your utility, from 547.7 to 547.6. If you were unlucky and lost your house, the loss of everything would have a much greater impact on utility. So you say yes to fire insurance. Even with modest wealth, the change in utility is slight, from 223.6 to 223.4. Now consider flood insurance. Suppose that $300,000 a year house is in the 50-year floodplain and it has a 0.02 chance of being destroyed in any 1 year. The expected value of insurance is 0.02 times 300,000, which is equal to $6,000. If you can find flood insurance for that amount or less per year, it's a good deal from an expected value perspective. Suppose flood insurance costs $5,000 per year. Will you buy? If you are wealthy, this may be worthwhile. Notice that utility decreases 4.7 points, from 547.7 to 543.1. If you're not wealthy, paying $5,000 has a larger negative impact on your utility, reducing it 11.5 points, from 223.6 to 212.1. That may be enough of a difference to make you say no to flood insurance, even though paying $5,000 for an expected return of $6,000 is worthwhile from an expected value perspective. And so, the theory changed from maximizing expected value to maximizing expected utility. The latest developments, noting many deviations from these theories and how people really decide, no longer reason from first principles like the 4 axioms of expected utility theory. Prospect theory followed the notion that people act to maximize their utility, but they added that positive changes to the status quo, or gains, are treated differently from negative changes or losses to the status quo. People dislike a negative change far more than they like an equivalent gain. In other words, losing $50 hurts worse than finding $50 feels good. Here the point is made graphically. With a gain of $50, psychological value increases 8.7 reference points. A loss of $50 reduces psychological value by 12.7 reference points. Prospect theory allows for the fact that individuals may choose a decision which doesn't necessarily maximize utility because they place other considerations above utility. Let's consider expected utility graphically. The utility of $4 is 2, and the utility of $16 is 4. The expected value of these two uncertain amounts of wealth is 1/2 times 4 plus 1/2 times 16, which is equal to 10. This is an uncertain quantity. The utility of $10 with certainty is 3.162. The utility of an expected value of $10, an expected wealth of $10, shown at point A, is only 3. This is also the utility of $9 with certainty. $10 with certainty yields more utility than expected wealth of $10 with uncertainty. A risk-averse person would be indifferent between $9 with certainty and the expected wealth of $10 with uncertainty. The difference between the uncertain wealth of $10 and the certain $9 is called the risk premium. In this case, the risk premium is $1. If the value of the uncertain asset exceeds the value of the certain asset by $1 or more, the person would be willing to hold the risky asset. Risk premium varies with the amount of wealth, by the way. It's not always $1. Let's use these ideas to consider some risk attitudes now. Imagine a game show where there are two doors. One door hides $1,000 and one door hides nothing. You can either choose a door or take $500. The two options have the same expected value of $500. No risk premium is being offered for choosing the doors rather than the guaranteed $500. Now, a risk-neutral person is indifferent between these two choices. A risk-averse contestant will choose the guaranteed $500. A risk-seeking person derives utility from the uncertainty and will choose a door. If most contestants are risk-averse, the game show might encourage the selection of the riskier choice by offering a positive risk premium. So if the game offers $1,600 behind the good door, it increases the expected value of choosing between doors 1 and 2 to $800. The risk premium in this case is $300. That would be the $800 expected value minus the $500 guaranteed amount. Contestants requiring a minimum risk compensation of less than $300 will choose a door instead of accepting the guaranteed $500. Notice from the shapes of the curves, the utility of a given amount of wealth will vary from one person to the next, depending on their risk attitude. Risk lovers like the gamble. Risk averters prefer the sure thing. Risk neutral people would be very comfortable with the thinking of Blaise Pascal.